Combinations of cells. More than one cell can be connected to obtain the desired value of current or voltage. There are three ways in which cells can be connected. 1. Series connection. 2. Parallel connection. 3. Mixed connection. We shall first consider the mixed connection and discuss series and parallel connection as a special case of the mixed connection of the cell. Mixed connection. A number of cells are connected in series and many such series connection of cells are connected in parallel with each other. Let us consider a series of n cells having EMF epsilon 1, epsilon 2 and so on, epsilon n, and internal resistance R1, R2 and so on, Rn. Let there be m such number of series of cells connected in parallel. The total EMF of each of the series combination of the cell EMF epsilon is equal to summation from I is equal to 1 to n epsilon I. The total internal resistance of the above series is equal to summation from I is equal to 1 to n Ri. The total internal resistance R of the mixed connection of cells is equal to 1 upon R is equal to m upon summation Ri. Therefore, R is equal to summation Ri upon m. The total EMF of the above circuit will be equal to EMF epsilon since all the series of cells are connected in parallel. Current I is equal to total EMF upon total resistance. Therefore, I is equal to summation epsilon I upon R plus summation Ri upon m. If epsilon I is equal to epsilon and Ri is equal to R, then I is equal to mn epsilon upon mr plus nr, where R is equal to the resistance connected in the circuit. 1. If there is only one series of the cells, m is equal to 1. I is equal to summation epsilon I upon R plus summation Ri. The equation gives us the formula for the current for series connection of cells. 2. If n is equal to 1, then we have parallel connections of the cells and I is equal to epsilon I upon R plus Ri upon m. Consider one simple connection. We are interested in calculating current flowing through resistor R. Applying Kirchhoff's first law at junction point A, we have I is equal to I1 plus I2. Applying Kirchhoff's second law to the closed path, A, C, R, D, B, epsilon 1, A. We have minus IR minus I1 R1 plus epsilon 1 is equal to 0. Therefore, IR plus I1 R1 is equal to epsilon 1. Therefore, I1 is equal to epsilon 1 minus IR upon R1. Similarly, from the closed path A, C, R, D, B, epsilon 2, A, we have I2 is equal to epsilon 2 minus IR upon R2. substituting the value of I1 and I2. In equation we have I is equal to epsilon 1 minus IR upon R1 plus epsilon 2 minus IR upon R2. Therefore, I is equal to epsilon 1 upon R1 plus epsilon 2 upon R2 minus IR into 1 upon R1 plus 1 upon R2. Therefore, I plus IR into 1 upon R1 plus 1 upon R2 is equal to epsilon 1 upon R1 plus epsilon 2 upon R2. Therefore, I into 1 plus R upon R1 plus R upon R2 is equal to epsilon 1 upon R1 plus epsilon 2 upon R2. Therefore, I is equal to epsilon 1 upon R1 plus epsilon 2 upon R2 upon 1 plus R upon R1 plus R upon R2. If more than two cells are connected in the above arrangement, let it be equal to n. Then, in general, I is equal to summation I is equal to 1 to n epsilon I upon Ri upon 1 plus R into summation from I is equal to 1 to n 1 upon Ri.